Hi, my name is Sergey Levine, and I'm going to talk about offline reinforcement learning, incorporating knowledge from data into RL. So, when we think about RL, maybe reinforcement learning for animals, maybe we think of something like this, right? So you provide reward or punishment, and as a result of that, you get some behavior, right? Maybe it's a behavior that is physically quite sophisticated. Maybe the sea lion needs to leap out of the water and peck at this object. But typically not very cognitively demanding, right? These are not behaviors that involve a lot of planning, a lot of deduction, not a lot of logic, right? That's perhaps the purview of higher animals, apes, humans. In his well-known report, The Mentality of Apes, Wolfgang Kohler described a particular experiment where a chimpanzee was placed in a room with a bunch of bananas suspended from the ceiling. The chimpanzee became a bit frustrated, couldn't reach the bananas, but then settled down, thought about the situation for a second, considered its possibilities, did some insightful planning, and deduced that it could actually pick up some crates in the room, stack them up, and then reach the bananas, right? Utilizing its prior knowledge of physics and how the world works. Or is that what happened? 50 years later, Epstein and colleagues conducted this experiment with a pigeon. A plastic banana was suspended from the ceiling, and the pigeon, wanting to reach the banana, became a bit frustrated, paced around the room for a while, contemplating possibilities. Eventually, the pigeon settled down a little bit, thought long and hard about the situation at hand, imagined some possible outcomes that could happen. Maybe performed something like insightful planning. Maybe even conducted a little experiment. And then after a while deduced that the way to perform this task would be to use the box that was placed in the room, move it a little bit into a location from which the pigeon could stand on the box and then reach the banana. Now, of course, the experiment is a little facetious. Pigeons don't have a particular affinity for plastic bananas, and besides which they can fly, so they don't need boxes to stand on anyway. The pigeon was trained, but the pigeon was never trained to perform the entire task. The pigeon was trained to peck at bananas and to move boxes separately. The composition of these skills to perform the entire task had to emerge on its own. It had to emerge through reinforcement learning. This is a reinforcement learning experiment. The pigeon was reinforced for individual tasks and figured out their composition. That is basically the idea behind what I'm going to describe in today's talk. I'm going to talk about how knowledge and common sense, things that seem to be the purview of planning, deduction, and logic, can emerge from data through reinforcement learning. Let's work with a somewhat less contrived example. Let's say that we want to build a household robot that will perform some cooking tasks. And in particular, we'd like to train it to chop an onion, right? So if you want to use reinforcement learning to learn to chop an onion, you have the robot hold the knife and you practice chopping the onion many, many times, and then it gets really good at chopping that onion, just like that sea lion got really good at leaping out of the water. When you then put this robot in a kitchen, and it's not holding a knife anymore, it's just told, go at it, perform the task. The robot will have no idea what to do. The skill was learned when holding the knife when there's an onion in front of it. Humans wouldn't have this problem. Humans have common sense. We know that if we were to find ourselves in that situation, you would rummage around in drawers, find the knife, find the onion, and then go at it, chopping the onion. But robots lack this common sense. They wouldn't figure out the individual steps. So here's how we can make it work, inspired by the pigeon. We're going to have data for our current task, which requires using the knife to cut the onion. And we're going to have prior data of other things we've done before. None of these prior things involve chopping onions, but they might involve opening a drawer. They might involve picking up an object from a container. They might involve picking up a knife from a drawer. If we utilize reinforcement learning algorithms based on dynamic programming, methods like Q-learning, these Q-learning methods will back up values, and they will figure out that the state where you are holding the knife is a high-value state. Similar states seen in the prior data will then also have high value. And the predecessors to those states will then also have high value. The dynamic programming process, combined with generalization from deep nets, will link up that prior data to the new task at hand and allow the robot to figure out that opening a drawer is a good way to pick up a knife which itself is a good prerequisite for chopping an onion, even if it's never seen that complete sequence before. Now, of course, in reality, our prior data might be more complex than that. It might involve some things that are not relevant to the task, maybe making a soup or cutting a carrot or baking bread. Crucially, we don't have to decide what is relevant or not. We can combine all of the prior data and let the Bellman backups take care of it. So in this scheme, Bellman backups link prior data to current task data. And it doesn't have to be a one-dimensional process either. You could have other tasks, like for example, opening a container that might contain some onions, and that could also be a prerequisite. Propagation of values through Bellman backups can connect prior knowledge to new tasks. But this requires us to be able to run reinforcement learning with past data. And that's actually surprisingly non-trivial. We don't want robots to have to revisit all those past kitchens, open all those past drawers repeatedly each time they learn a new task. We want to collect that data, store it once, and then reuse it for all of the tasks that we're going to learn. And that requires something called offline reinforcement learning. Standard reinforcement learning operates on policy, which means that we collect some data, use that data to improve our policy, then throw it out and use the improved policy to collect more data. We can extend this to the off-policy setting, where all the data that we've collected can be stored in a buffer. But we still need to use the latest policy to collect additional data. Now you could say, well, maybe we just stop doing that. Maybe we just store that data and we don't redeploy the new policy. It turns out that with conventional off-policy RL methods, that's a very bad idea. It works very poorly, and I will explain why shortly. There's actually a very good reason for it. What we want ultimately is offline RL methods. Methods that can use data that was collected before using any policy or combination of policies and utilize that data to train up a new policy without going back to interact with those past environments. Perhaps we collected a large data set from past interaction for all the stuff that we've done before. We're going to store it to disk and then use it to learn policies for our new task. Now, if our new task requires some task-specific experience that we didn't have, maybe we've never actually seen onions before, we could collect some more data of that particular task in a particular narrow context. But we're still going to be relying on the bulk of that past data for generalization to new contexts, new initial conditions, and so forth. So to make this possible, of course, if we can do this, we can enable robots that have broad generalization. We could also make it possible to apply reinforcement learning to a wide range of problem settings that are infeasible with on-policy or conventional off-policy methods. Settings like, for example, prescribing treatment plans for patients. Settings where you don't want to do active exploration and data collection. Settings like constructing plans for scientific experiments, maybe controlling a power plant or logistics networks, and so on. So in today's talk, I'm going to describe two topics. I'm going to talk about algorithms for offline reinforcement learning. Why is offline reinforcement learning difficult and how we can derive effective methods for it? And then I'll describe how offline RL methods can be used to acquire this kind of knowledge or common sense that I alluded to in the beginning of the talk. But first, let's start with the algorithmic foundations. I'll begin with a quick primer of Q-learning. Those of you that are familiar with RL might find this to be mostly review, but I'll go over it anyway to make sure we're all on the same page. In reinforcement learning, you have an agent that interacts with the world by selecting actions. We'll call these A. And the world responds with states S, and perhaps a reward R. Our goal is to learn a policy pi, which gives us a distribution over actions conditioned on states. And the RL objective is to maximize the total expected reward. A very useful object for doing this is something called the Q function. The Q function is specific to a particular policy pi, and it tells us if we start in a particular state st and then take an action at, what will be the total reward that we'll get if we then follow the policy pi. If we can acquire such a Q function, we can then determine the optimal policy simply by taking an action with probability 1 if it is the argmax of the Q function. This is the basis of policy iteration. We can also skip the middleman and learn the optimal Q function directly. To do this, we simply have to enforce that the Q value at a particular state action tuple is equal to the reward at that tuple plus the max of the Q value at the next state. So if we enforce this equation at all the states, we'll acquire the optimal Q function, and from that, we can determine the optimal policy. One way we can do this is we can simply minimize the squared difference between the left-hand side and right-hand side of this equation. I'm going to use the letter y to denote the target value, which is the right-hand side of the equation, in the remainder of the talk. So based on this principle, we can derive an off-policy RL algorithm. See, we don't need on-policy data to enforce the Bellman equation. We can simply enforce it for all state action tuples we've seen before. So an off-policy Q-learning algorithm would look like this. Collect a data set using some policy and add it to your buffer. Sample a batch from that buffer, and then minimize the difference between the left-hand side and right-hand side of the Bellman equation on that batch. We can visualize this graphically by saying that you interact with the world to collect some data, and that goes into your buffer, that goes into your bucket of transitions. And then you're going to be crunching away on this bucket of transitions, improving your Q function. You could go out and collect more data with your latest policy whenever you wish. However, if we're doing offline RL, then we would skip this step and we would rely entirely on that initial data set that was collected before. We would rely entirely on past data. So, does this recipe work? It seems very logical, very sensible. Does it produce good results? Well, first I'll tell you about some experiments to study Q-learning algorithms in general that might illustrate maybe some of the issues that occur, and then I'll discuss those issues in much more detail. So first, I'll tell you about an experiment that we conducted at Google on large-scale robotic learning with RL. This is a system called Qt-opt, and it is learning through a combination of offline data and on-policy collection. So we have multiple robots that are collecting data together. They're pushing that data into an on-policy buffer and simultaneously pulling data from past experiments, many of the past experiments we've done. The system works very well. It can perform a wide range of robotic grasping tasks, including under perturbations, in dense clutter, with transparent objects, difficult objects, and entirely new objects that were never seen before. These are our test objects. But one of the things we did in these experiments is that we measured the difference between purely offline training versus training where we allowed the policy to fine-tune with some additional online collection. The data set for the offline training consisted of 580,000 transitions. The fine-tuned version fine-tuned for an additional 28,000 transitions. So the difference in dataset size is minuscule. It's only about 5% more data. The success rate for the offline version was 87%. The success rate for the fine-tuned version was 96%. Now you might say these are both doing very well, but if you consider failure rates, basically 100 minus this, the failure rate for the offline version is more than 3 times larger. And it can't just be the amount of data. The amount of additional data is minuscule. So something about training offline makes the policy a lot worse. 2 of my students, Avril Kumar and Justin Fu, wanted to study this problem in more detail, so they examined a simpler benchmark task, the half cheetah. And they compared the performance of naive off-policy RL when used in offline mode with different sized data sets. Their initial hypothesis was that maybe the problem has something to do with overfitting. If you keep training on that offline data, maybe eventually you overfit to that data, and that's why you get the bad results. The blue curve here shows training on 1,000 points. The red curve shows training on 1 million points. If the problem was overfitting, you would expect performance to get better as the dataset size increases, and that is not what we see here. We see that all dataset sizes are at around minus 250. Now, one idea that Avril and Justin had was that perhaps we can look at how well the Q function itself thinks it's doing. Remember that the Q function is estimating the expected reward to go. So if you look at the Q values at the initial states, that tells you how well it thinks it's going to do. And here's the plot of that. The y-axis here is a log scale, which means, for example, for the red curve, the Q function that gets minus 250 when it's used to control the agent thinks it's going to get 10 to the 7th power expected reward. Whoa, that is massive overestimation. So the Q function, for some reason, thinks that it's going to do extremely well, and in fact ends up doing very poorly. There's actually a very good reason for it. In fact, once we understand this reason, we will understand that the problem is inevitable. Let's take the Bellman equation, and let's rewrite it in a slightly different way that is exactly equivalent. Instead of writing it as a max, I'm going to write it as the expected value over the next Q function under a distribution pi nu, where pi nu is that argmax distribution, so it assigns a probability of 1 to the argmax. This is exactly the same, it's just a different way of writing it. Now, when we're evaluating the expected value of some learned function under some distribution, we know that if this distribution is similar to the training distribution, we'll get the right answer. So how is the Q function trained? Well, the Q function is trained to regress onto target values in expectation under the distribution that created our data set. We call this the behavior policy pi beta, right? Because that's where our data comes from and we train it on the data. We're doing expected risk minimization. When we do expected risk minimization, we expect to get the right answer under the same distribution as the one we train on, right? So this is our target value, this is our behavior policy. But we're evaluating it under the distribution pi nu. So we expect good accuracy when pi beta is equal to pi nu. But how often does that happen? Right? The whole point is to select pi nu to be better than our behavior policy, which means that it will be systematically different, which means that we will experience distributional shift. But the situation is actually even worse. You see, we don't just select any pi nu, we select it to be the R max with respect to pi of the expected value of q. Imagine the green curve represents the true function and the blue curve is a fit. If we select x to maximize the predicted value, even though the blue curve is a good fit, we'll select exactly the point where it fits worst, where it has the largest error in the positive direction. This is very similar to the phenomenon of adversarial examples. The policy is in a sense being an adversary to the Q function. It's trying to find the actions for which the Q function will erroneously predict the largest possible value. And these kind of adversarial situations are very difficult to deal with. Certainly conventional ERM does not deal with them, and that's why we see this massive overestimation when we run Q-learning. Once we understand the problem of distributional shift, we understand that this issue is inevitable if we use naive off-policy Q-learning methods. So how can we mitigate this issue? Well, there have been quite a few offline RL algorithms proposed in the literature, but I'll discuss one particular method that we've developed recently called conservative Q-learning that I think works particularly well. The idea in conservative Q-learning is to directly combat this overestimation problem. So remember, the issue can be visualized like this. If we have a Q function that we fitted to our true signal, the true signal here in green, the learned Q function in blue, we want to get rid of these spurious peaks, these places where the Q function thinks the Q value is better than it really is. The way we'll do this is by taking the standard Bellman error minimization objective and combining it with a regularizer that specifically pushes down large Q values. So here the distribution over actions mu is selected to specifically maximize Q, and then Q is minimized under that distribution. So mu finds these spurious peaks, and then the regularizer pushes them down. In fact, we can show that this procedure produces a Q function that is always less than or equal to the true Q function for a large enough alpha. So this procedure results in a Q function that is provably a lower bound on the true Q value as long as the regularizer is chosen appropriately. This immediately suggests a mechanism for learning policies. Learn this lower bound Q function for a current policy and then find the policy that maximizes it. In fact, we can develop a better bound. If we modify this regularizer, which always pushes down on Q values, with another term that always pushes up on the samples in the data. This might seem strange at first because we're trying to combat overestimation, and for some reason we're actually pushing up on Q values. But if the high Q values are all for points that are in the data set, these two terms will cancel out. So the only time when mu will actually push down on Q values is when it finds high Q value actions that are outside of the training set. So this will push the policy towards the training distribution, and as it gets closer to the training distribution, the effect of the regularizer begins to cancel out more and more. This no longer gives us a pointwise bound for all SA, but we can still prove that we are guaranteed to have a lower bound in expectation under our learned policy, which is all we really want because all we want to do is evaluate our policy. So the bound holds in theory, does it hold in practice? What we're going to measure is the difference between the estimated Q value and the true Q values estimated with Monte Carlo returns. We're testing it on some benchmark tasks, and you can see here that both CQL variants have negative errors, which means that they are all less than the true Q values. CQL-H is the more advanced version on the previous slide. CQL equation 1 is the more primitive version with just the minimization term. You can see that the more advanced version has a tighter bound. The true Q values are on the order of a few thousand, so errors of -10 or -40 means that we're getting very accurate Q values. Prior methods based on ensembles and other prior offline RL methods generally overestimate massively. They have wild optimism. So we're doing a lot better with CQL. How does CQL compare in experiments? Well, we evaluated CQL on the D4RL benchmark suite, which is a pretty difficult benchmark suite intended to evaluate offline RL methods. The kitchen tasks involve using a robotic arm to manipulate drawers and kettles and things like that in the kitchen. The adroit tasks involve controlling a 5-finger hand. And the and maze tasks require stitching together parts of different trajectories to construct longer sequences, much like the onion chopping example in the beginning of the talk. It should be noted that on the and maze tasks, especially the medium and large mazes, basically nothing works. So these scores are normalized between 0 and 100. On the Android and kitchen tasks, the strongest prior method is actually behavior cloning, directly copying the data. Prior offline RL methods generally fail to improve on that. CQL attains state-of-the-art results across all of these tasks, with just a couple exceptions, and almost a couple exceptions for the Android task. It's actually behavior cloning that is the strongest alternative method. So it's up to 5x better on some of the tasks, 50 to 300% better on others, 10 to 30% better on the kitchen tasks, and essentially infinitely better on the and maze tasks because it's the only thing that does anything at all. On Atari games, we also evaluated this on the 1% dataset from Agarwal et al., which is the most difficult dataset, and again we see improvements 50 to 600%. So CQL seems to work pretty well on many, many different tasks. And we seem to know why it works well. We seem to understand theoretically this lower bound property. There's still plenty of room for improvement on these tasks, but we have a tool at our disposal now that we can use to solve offline RL problems. So let's see how we can apply this tool to acquire knowledge and common sense from prior data. So to remind you, this is what we're going to try to do. We're going to try to link data for our new task to prior data that will help us generalize to new initial conditions to meet those preconditions by performing other behaviors. Specifically, imagine that you have this task, picking up a ball from an open drawer. If you train on just this task, and then at test time the drawer is closed, your policy won't know what to do. So we're going to see if we can include prior data that exhibits other behaviors, none of which involve picking up the ball from an open drawer, but they might involve other things like moving other objects, opening drawers, closing drawers, opening other drawers, and moving other objects. The setup is that our task has a 0-1 reward, meaning the reward is 0 unless you perform the task successfully, at which point you get a 1 at the end. You have to learn the task entirely from raw image observations, and we're going to actually be testing it on real robots later too. And you only see the final task that you want to learn from a single starting condition, in this case, just the open drawer. Now, the prior data has no task reward at all. All rewards in the prior data are 0. It doesn't accomplish the new task at all either, so the only way to connect up the prior data to the new task is through those Bellman backups. But the prior data does show you how to reach useful states. It also shows you many useless things as well. The algorithm is very simple. We're just going to run Q-learning, conservative Q-learning, on this combined data set. So here are the results. These are the empirical results, but I think it's clearer if I actually visualize it. So this is the training task, picking up a ball from an open drawer. If you combine it with diverse prior data, then at test time you can figure out that if the drawer is closed, you should open it and then pick up the ball, even though you've never seen that complete sequence before. You've never seen a complete sequence that involves opening a drawer and picking up the ball. If the top drawer is open, you first close the top drawer, then open the bottom drawer, and then pick up the ball. You've never seen closing the top drawer and opening the bottom drawer. You've certainly never seen the whole sequence, but you can still put the pieces together. If there's an object in the way, pick up the object, put it somewhere else, then open the drawer, then pick up the object. We can do this in the real world too. So here the task involves taking a stuffed animal out of an open drawer, and the prior data involves opening and closing the drawer. Putting those together, the robot can actually figure out at test time that it should open the drawer and then try to pull out the stuffed animal. It doesn't work every time. Here the success rate is roughly 2/3. So you'll see that one of the trials fails, the other two will succeed. But seems to work pretty well from raw images, directly using real-world training data. All right, so where am I going with all this? Well, I think that offline RL provides us with a really powerful way to incorporate diverse data into reinforcement learning. And when we do this, we get knowledge that is represented and acquired implicitly through Bellman backups, which link recent experience with prior experience. So the system has knowledge. It's just that knowledge is not stored explicitly. It's distilled from the data via RL into the policy and into the Q function. This results in generalization. The generalization that resembles a kind of common sense. When the drawer is closed and you need to pick up the object, first open it. So perhaps this is what we need to get broad generalization. Perhaps if we want to encode knowledge into our reinforcement learning systems, what we really need is large prior data sets and algorithms that can utilize those data sets for offline training. Thank you very much for listening. I'd like to especially acknowledge two of my students, Aviral Kumar, who led the work on conservative Q-learning, and Avi Singh, who led the work on COG, the algorithm for combining those prior and new data sets. Thank you, and I'd be happy to take questions.